Okay, so the first thing we want to do is try to set up ladder operators much in the same way we did with the harmonic oscillator. So the idea is that there's an operator A hat such that when you act on the eigenstate of LZF, it provides a new eigenstate of LZ with slightly different eigenvalue. So LZ acts on A hat F, and it equals M plus delta M A hat F. Well, we can expand this out as M A hat F plus delta M A hat F. But M is just a constant, so we can bring it on the inside here. A hat M F plus delta M A hat F. But this is just LZ acting on F. Well, we can subtract A hat on LZF from both sides, and we just get the commutator of LZ with A hat acting on F equals delta M A hat F. And like with our harmonic oscillator, our two special operators are Lx and Ly in place of P and X. So we're going to propose that A hat is of the form A hat equals P Lx plus Q Ly. Hats, where P and Q are constants. So LZ, and we can remove F now from that equation. So LZ with Lx, PLx plus QLy is equal to delta M PLx plus delta M QLy. And if I forget to put hats, my bad. So we can break this up. LZ Lx times P plus Q times LZ with Ly. Well, based on our commutation relations, that's just IH bar times P times L sub Y plus, and that is just negative IH bar Q LX equals delta M P LX plus delta M Q Ly. Now we're going to equate the Lx and the Ly terms. And that means that IHP must equal delta M times Q, and negative IHQ equals delta M times P. So in this equation, we're going to multiply delta both sides by delta M. IH bar delta MP equals delta M squared times Q. With that we know is just negative IH bar Q, and then IH, I times negative I is just 1, equals H bar squared Q equals delta M Q. Well, you can cancel out the factor of Q. We don't want Q to be 0, so that means that H bar squared equals delta M squared. In our case, that gives us two possibilities. KH bar equals delta M, where K is equal to positive 1 or negative 1. So IH bar So KHQ delta M times Q is equal to IH bar times P. And cancel out H bar. And K squared is just equal to 1, so we can do K squared and then divide it up by K. So I times K, IKP is equal to Q. So now we can write our ladder operators as LXP plus IKLY. Now we have two different ladder operators, one for K equals plus 1 and one for K equals negative 1. If K equals plus 1, our eigenstate is raised by an amount, H bar, and if K equals negative 1, our eigenstate is lowered by amount, H bar. So let's see how this changes our L squared eigenvalue. So let's act L squared on A hat K sub K F equals, well, we can write L squared acting on AK is equal to the commutator of L squared with AK, A sub K, plus AK acting on L squared. And then we'll act it on F. Well, A sub K is just LX plus IKLY, so you're basically just having L squared with LX plus something times L squared with LY. And that's just 0. And we already know that L squared acting on F is just lambda F. And lambda is a constant, so we can pull this out. So we have this equation here. When L squared acts on this new state, raised or lowered state, its eigenvalue does not change, which implies a degeneracy, which is distinct from the harmonic oscillator, of course. And this is a useful fact that will lead us into the next video.